Welcome back to the deep dive. Our mission here is to take the complex source material you've shared and, well, find the connections you didn't even know you were looking for.
And today we have a fantastic one.
We really do. We're looking at one single word that connects two completely different worlds: regression.
It's amazing, isn't it?
Yeah.
On one hand, it's the absolute foundation of modern statistics. It's
Mhm.
the engine behind AI, economic forecasts, everything.
And on the other hand,
It's the term for a technique that claims to recover memories of past lives.
that contrast is exactly what we're digging into. We want to unpack what certainty even means when you're dealing with, say, an unmeasurable past versus a mathematically calculated future.
Before we get into all that, it's probably worth grounding ourselves in where the term even came from.
Yeah, good idea.
Because it's pretty old, at least in the world of stats. It was coined back in the 19th century by Francis Galton. And he wasn't talking about data or AI.
He was the biologist, right? He was looking at heredity.
Exactly. Galton used regression to describe this biological phenomenon he noticed. The idea that children of parents with extreme traits,
Like being exceptionally tall.
right, those children would tend to have heights that, well, they would regress down toward the normal average for the whole population.
So it's this idea of returning to the mean,
That's the origin, a return to a stable, measurable average.
which is a perfect segue because the first kind of regression we're going to talk about deals in things that are almost completely unmeasurable.
Past life regression, PLR.
And the belief behind it is surprisingly widespread.
It really is. Globally, belief in some kind of afterlife is common, but reincarnation specifically is strong in many cultures. I mean, you look at a country like Mexico, 76% of citizens believe.
And even in Western Europe, it's around 20%. The sources also pointed out that for people who call themselves spiritual but not religious in the West, it's 38%.
That's not a small number. And that belief really matters because it changes how people see the world, how they cope with things like trauma or, big existential questions.
Okay, so let's draw a really clear line here between the, let's say, therapeutic technique and the rigorous academic study.
A crucial distinction.
What is past life regression in practice?
So PLR is the practice of using hypnosis and some suggestive questioning to try and recover these alleged memories of past lives.
And what's the mainstream medical take on that?
Oh, it's widely discredited. Medical practitioners don't see these as facts. They see them as fantasies, delusions, or most often what are called confabulations.
What makes a memory that comes up during hypnosis so untrustworthy?
It's all about how it's fabricated.
Yep.
Memories are constructed, often without the person even realizing it. The imagination pulls from a couple of key sources.
Okay.
One is cryptomnesia. That's basically forgotten information you picked up somewhere, like a movie or a book. The other is, well, suggestions from the hypnotist.
So if I saw a documentary on WWII a few years ago and totally forgot about it, under hypnosis, my brain could just weave that into a personal story.
Precisely. And here's the scary part. Once that fabricated memory is created, your brain can't tell the difference between it and a real one. In fact, people often report that these constructed memories feel more vivid, more real than their actual life events.
Oh, there was that anecdote in the sources that
Hey.
it perfectly showed this.
The Japanese fighter pilot,
Yeah.
a subject under regression, claimed to be a pilot in World War II.
But when they were asked a really basic question,
The name of the emperor at the time, Emperor Hirohito, they had no idea.
so the whole narrative was just patched together from, what, war movies, general knowledge?
Most likely, it shows how flimsy the factual basis can be.
Okay, so that's PLR. Let's pivot to the academic side. The investigation of cases of reincarnation type or court. This is different. This is scholarship.
It is. This work was really pioneered by a psychiatrist named Ian Stevenson at the University of Virginia. He documented over 2,000 cases with a very systematic, methodical approach.
And when academics reviewed all these studies, what did they find?
Well, a big review of 78 studies showed a clear focus. 84% of the cases were children. Geographically, most of the work was done in Asia.
Were there patterns?
Fascinating ones. Kids usually start talking about a past life around 35 months old. In about 75% of the cases, they described how they allegedly died.
And there's a phobia connection.
Yeah, 35% of those kids had phobias that seemed directly related to that mode of death.
The biggest challenge here has to be just ruling out normal communication, right? How do you prove the information wasn't just passed along?
That is the single most critical control. Researchers would do first-hand interviews, check documents. But the real gold standard was getting a record before contact was ever made.
So writing down what the child said before anyone tried to find the supposed former family.
Exactly. And only 11% of the cases reviewed actually met that standard. It's so vital because without it, you just can't rule out that the information came from somewhere else.
So whether it's suggestion in a therapy session or just accidental communication, the danger is identical.
It is.
You're treating an unverified, maybe even constructed input as if it's a solid fact.
And that gets us to the ethics of it all.
Yeah.
PLR, as a practice, has been heavily critiqued for violating that core medical principle of first, do no harm.
Because it makes people vulnerable to these false memories.
And those memories feel so real that the process itself can cause psychological damage, especially when it's sold as a form of healing.
You know, that idea, the danger of mistaking a fabricated input for a fact, that's the perfect bridge to our second topic.
Statistical regression.
Exactly. Because in the world of AI, the inputs are data, not memories. But the risk of measurement error leading to completely flawed conclusions, it's just as real.
The fields couldn't be more different, but the fundamental challenge, how to handle uncertainty in your inputs, is exactly the same.
Okay, so let's make that pivot. What is statistical regression in the context of modern data science?
At its core, regression analysis is the workhorse of any quantitative field. It's a method you use to estimate the relationship between an outcome, the dependent variable, and one or more predictors.
So does X cause Y?
Or at least is X related to Y. It's used for two main things: prediction, so forecasting, and trying to infer some kind of causal relationship.
And now, with AI and machine learning, researchers are using it in a new way, a way that's causing some big problems.
It's a very big problem. It's called the two-step strategy.
Walk us through it. What are the two steps?
Okay, step one. A researcher uses an AI model like an LLM to generate an estimate of some variable that's hard to observe directly. We can call this estimate theta hat.
So the AI is classifying millions of job postings to see if they're remote or not. That classification is theta hat.
Perfect example. Then, step two, they take that theta hat variable and they just plug it into a standard regression analysis. They treat it as if it's a perfectly measured, 100% accurate fact.
And why is that a huge statistical mistake?
Because theta hat is not the perfect fact. It's just a proxy for the real variable, theta. And that proxy introduces measurement error. If that measurement error is significant compared to the other uncertainties in your regression, it completely invalidates your inference.
What does invalidates mean here? What breaks?
Your standard errors, your confidence intervals, the very tools you use to decide if a result is real or just noise, they become inaccurate.
So you might think you found a huge significant effect when it's not there.
Or, and this happens a lot, you drastically underestimate the true sides of the effect. It masks the real story.
This sounds like it feeds directly into the replication crisis we hear so much about in the social sciences.
It's a major contributor, absolutely. You see these studies get published, but when other teams try to reproduce the results, they can't. And this issue, not accounting for AI measurement error, is a growing reason why.
Let's make this really concrete. The sources break down 3 ways this happens. Let's start with the first one, label imputation.
Right, this is the job posting example we just mentioned. Researchers used a large language model to label hundreds of millions of job postings as either remote or not remote.
And the model was good? The accuracy was what, 98 or 99%?
Phenomenal accuracy. In almost any other situation, you'd celebrate that and move on.
But not here.
Not with this much data. So when they did the simple two-step regression predicting wages based on that remote label, they found remote jobs were associated with a 36 log point increase in wages.
For our listeners, what does a log point mean in simple terms?
You can think of it like a percentage change, so a significant pay bump for remote work. But then the researchers went back and applied sophisticated bias correction methods to account for that tiny 1–2% error rate.
And when they corrected for the error?
The estimated effect jumped by 76%. It went from 36 log points to 64.
Wow. So the takeaway is that even 99% accuracy can be misleading.
It's inconsequential when you're working at that scale. That tiny bit of measurement error was of first-order importance, and it made them dramatically underestimate the real wage premium for remote work.
That's a powerful example. Okay, what's the second type of AI input?
Dimensionality reduction. This is where you use AI to find a core concept hidden in really complex data.
The CEO diaries example.
Exactly. Researchers had these diaries with 654 different activity combinations. They used an AI model to analyze all that and extract a single behavior index, basically a score for that CEO's leadership style.
And what did this simple two-step regression show?
It showed that a higher score on this leadership index was linked to a 40 log point increase in the firm's sales. But what's really interesting is that when they applied the correction methods, the result was pretty much the same.
Oh, so it didn't change. That's the complete opposite of the remote work study.
It is, and it's a critical point for you to understand. This kind of bias isn't inevitable. It all depends on the specific situation, how big the AI's measurement error is compared to all the other noise in the data you're studying.
Okay, that makes sense. Let's get to the third type, index construction. This is where AI reads text and creates a score, like for sentiment.
A very popular tool in economics. In this case, researchers built an index for hawkish sentiment in the written statements from the Federal Reserve, the FOMC. They used a BERT model, which had about 85% accuracy on its test data.
So a bit less accurate than the job posting model. And what happened when they used the flawed two-step method here?
They took their sentiment index and tried to see if it predicted the market's reaction. The two-step regression found only a weak, barely positive effect, and the model's explanatory power, its R-squared, was tiny, 0.0425.
So basically, the model said the sentiment index didn't really explain market movements at all.
Pretty much. But, and this is the kicker, when the researchers reran the analysis using the robust joint estimation method, which is the gold standard for this kind of correction, everything changed.
How so?
The estimated effect size of that sentiment score nearly tripled, and the R-squared value also tripled, jumping up to 0.1429.
That's an incredible difference. The two-step method wasn't just a little off, it completely missed the relationship.
It did. Treating that 85% accurate classification as a perfect fact just diluted the signal so much that the true economic impact of the Fed's language was almost invisible.
So we know the two-step strategy is flawed and common. What are the actual solutions? How do researchers get valid results?
Well, there are two main alternatives that are being proposed. The first is bias correction, which we mentioned.
Right.
It's simpler, it's scalable, but the catch is that the formula you need is very specific to the model you're using. It's not one size fits all.
And the second one, the one that produced that huge result in the Fed study.
That's joint estimation. It is much more difficult computationally. It requires some pretty advanced statistical methods, things like Hamiltonian Monte Carlo.
But it's worth the effort.
The simulations show it is. It produces the most reliable results, the lowest risk, and confidence intervals that you can actually trust. It's the approach that truly accounts for all the upstream uncertainty from the AI model.
So if you want certainty, that's the path.
That's the closest you're going to get.
This is the perfect place to shift from the technical problem to the ethical one. Where does this search for statistical certainty have the biggest real-world impact?
Let's talk about the insurance industry. Their entire business is built on predictive analytics, on regression. And now they're using data from, telematics in your car or your smartwatch to personalize pricing.
Which sounds good for low-risk people. They get lower premiums. Fair enough.
It sounds fair on the surface. Yeah. But this level of precision creates a really deep moral dilemma.
Which is?
Models trained on historical data can accidentally perpetuate societal biases. For example, using a zip code as a proxy for risk might just be punishing people for living in a poorer neighborhood, not because of how they actually drive.
And these models are black boxes, right?
Often, yes. They're so complex that even the insurer can't fully explain why the model made a specific decision, and that just erodes customer trust.
But the deepest conflict here is between that need for profitable precision and what the industry's role as a social safety net.
That is the core tension, exactly. If your models can identify a high-risk group with near-perfect statistical certainty, it might make insurance completely unaffordable for them. Or they might not be able to get it at all.
Which undermines the whole point of insurance.
It challenges its fundamental societal role, which is to support vulnerable populations. You have to balance the need for risk-based pricing with that social contract.
So if the data is so powerful, what's the solution? Is it just less data?
No, the sources are clear that the answer isn't just better math or less data. It's human oversight, it's judgment.
The underwriters have to be able to step in.
They have to be empowered to critically assess the model's output and apply ethical judgment, to say, no, this outcome is statistically correct but systematically unfair. That means you need teams with data scientists, underwriters, and ethicists all working together.
We started this deep dive with regression as a search for an unmeasurable past, where suggestion could create a false reality.
And we ended with regression as the foundation of our predictive future, where uncorrected measurement error can create a biased and unfair reality.
So what's the core takeaway for everyone listening who works with this kind of data?
It's simple. Don't default to the two-step strategy. Never treat an AI's output as a clean, perfect fact. That measurement error is real, and if you don't use rigorous methods like joint estimation to account for it, your conclusions could be fundamentally wrong and potentially very harmful.
Which leaves us with a final, provocative thought for you to take away. If these advanced regression methods allow us to identify high-risk individuals with near-perfect statistical certainty, how much ethical judgment must we consciously apply to override a statistically proven outcome, all in the name of upholding a societal safety net?
When does our ethical duty require us to ignore what the data says is certain?
We'll leave that question with you. We'll see you on the next deep dive.